Okay, we discuss Cauchy problem for general elliptic operator here, I mean variable coefficient second order operator. So, for that what we do is that we, as before, we consider terminal data which is taking, I mean multidimensional, so R d to R, and G is the function which is taking time and the space value, okay, and giving me a real value, and K, the potential function, is non-negative, and this is taking time t and space value to give me a non-negative value, and this A, F, G, K are assumed to be continuous. In addition to this, I also have further two more conditions, that mod of f is less than or equals to L times 1 plus norm of x to the power 2 lambda for some lambda. So, this is, as I mean similar, I mean is equivalent of saying that f has at most polynomial growth. So, here the degree of polynomial will be 2 lambda. So, I mean at most 2 lambda degree of growth. Okay. So, here I am not writing explicitly that is a function of x, but it is understood that I want to mean that, and here also this is a function of t and x. So, modulus of these things is less than or equals to L times 1 plus norm of x to the power 2 lambda. So, that means that f and g, since they are functions of two variables, correct, time and space is unbounded. So, on that space I need to define that what type of function it is, because just continuous functions, all continuous function on unbounded space are they are not bounded, and then sup norm would not work. So, okay. So, so here we are clarifying the class of functions what we are considering here. So, we are considering that f and g are having at most polynomial growth in the space variable, okay. But on t we do not need to put any growth condition, because it is compact set, correct, it is bounded, okay. So, for every other x, okay. So, here g as a function of time, it is bounded actually, okay. So, this is these are the conditions on f and g, okay. Then there is the result says that if v is a continuous function on this 0 to t r d. So, on the time and space it is continuous real valued function, and also once continuously differentiable in first variable, that is time variable, and twice continuously differentiable with respect to the space variable, okay. And also this v solves this equation. This equation is del v del t plus a t v plus g is equal to k v here. So, here this a is the operator which comes which is associated with the s d, which is d, that d x t is equal to b of t x t d t plus sigma of t x t d w t. I am not talking about here the functional SD, I am just talking about the SD here, okay, and is equal to kV, okay. So, this equation should be satisfied by this function v on this close 0 to open t close R d, okay. So, here, and at the terminal time the unknown v should satisfy the terminal condition, that it should match with f, okay. Good. And then in addition to that, we also want to look for solution in a particular class, the class of functions with at most polynomial growth, okay. Now, thing is that if you assume that we have a solution to this problem in this class, okay, in this class, then for every time t and x in this set 0 to capital T, this thing across R d, this v, the solution of this problem has a particular expression, okay, it has a representation. So, this can be written as using conditional expectation, okay, where I would be able to use solution of stochastic differential equation, okay, which stochastic differential equation with the same, which involves exactly the same parameters which appear in definition of the operator script A, okay. So then for every Tx in this time and space domain, Vtx is given by expectation of terminal time f of capital T e to the power of minus small t to capital T k u x u du plus integration small t to capital T g s x s into e to the power of minus small t to s k u x u du ds, given x t is equal to small x. Okay. So, here we must connect this result with the result what we have previously obtained in the Feynman-Kac theorem. There we have not considered a variable coefficient general second order elliptic second order differential operator. We have taken half times Laplacian. Okay. So, then there we have obtained exactly similar expression, but instead of x, Brownian motion appeared, but here we have a general this operator. So, this involves the coefficients of which appears in which appear in the SD, and therefore, the solution of this problem is written as conditional expectation of functional of the stochastic process, which is solution of the SD. Okay. So, here trivially one can see that, okay, if at small t is equal to capital T, this satisfies this terminal condition. So, let us check it easily. Okay. So, if you put small t is equal to capital T, then this part disappears. So, e to the power 0 is 1, and here this integration also disappears, okay, because integration small t to capital T. So, what you would be left with only expectation of f of x capital T given x capital T is equal to small x, because small t is equal to capital T, correct. So, given x capital T is equal to small x, expression of f of x capital T is exactly f of x. So, you would get f of x here, but inside the domain in the interior, why should be the expression of the solution of this equation needs a detailed proof. So, we are going to see the proof now, but before seeing the proof, we need to establish one more result that we are going to do first, and then we would come back to this result and we prove this thing. Okay. It is apparently clear what should be the methodology, because for special case where A was just half times Laplacian, there we have seen the proof, that was just nothing but application of Ito's formula. Here also we are going to do that. Only thing is that we have to be careful for passing to the limit, okay, appropriate manner, so that things make sense. Okay. So, let B I and sigma I j are progressively measurable functionals from time domain and path. So, here I am taking the general setting where FSD is considered, okay, B and sigma are functions of paths, okay, are having at most linear growth condition. Okay. So, here we are having say linear growth condition, Okay. So, this is a space of all continuous functions from this non-negative time to R d. So, that means R d valued paths. Okay. So, B is a function of time and R d valued paths. Earlier B sigma were function of t and position of the process. Now, B and sigma are function of time and the whole realization of the process. Okay. So, that is the kind of thing. So, having at most linear growth condition. So, this is the condition we keep here. So, y is a particular member in this path space of paths. If this triplet is a weak solution to FSD. Okay, this triplet is XW, this is a solution, and this is the filtered probability space, the weak solution with finite moment initially, that means the starting x0. So, there is some m. Okay, so that, I mean, so the expression of this is finite for some n. Okay, then for any capital T, finite and positive capital T, there exists some C such that, so C of course depends on the choice of M, T, K, D, etc. So, such that expectation of maximum of modulus xs, okay, to the power 2m. So, here you see that this is 2mth order moment. Okay. So, I am writing that for not only 0, I am saying here say s is running from 0 to t, and then the 2mth power of xs, okay, I mean norm of xs, and maximum of all these. Okay. So, highest point during the path of 0 to t. Okay, and expectation of that. Okay, expectation of that thing, one can still get that less than or equal to that constant times that this number, expectation of x naught to the power 2m times e to the power of c t, that this c appears there. Okay. I think here by mistake is small c appears, yeah, but yes. Okay. And here this t is the same t as here it appears. Okay. And expectation of, so yeah, and small t is any number which is less than or equal to capital T, and then this c can be kept intact, thus this c does not depend on t. That is very important, correct? Okay. So, here the second result is that expectation of x t minus xs, that is increment. So, so 2mth order moment of increment, this is the thing, okay, is less than or equal to c times 1 plus expectation of x naught to the power 2m, which appears here, times t minus s to the power of m. Okay. So, with respect to increment also we can get some estimate here. So, these are very important things so what we have obtained due to these properties of the FSD. Okay. So, here we are going to prove these theorems first, okay, these result, and then we are going to use it. We would use actually this result extensively. Okay. So, proof starts here. For this proof we would first use this inequality. So, this is the inequality what we are going to use. So, let us derive this inequality. So, I have a1, a2, an, some real some scalars, and then mod of ai to the power p is less than or equals to the pth power of the sum, because this is only one particular I. So, this is type of a1, a1, a2, etc., an. So, this is the one particular thing. For every I which is between 1 to n, this is true of course, because this right hand side has more number of non-negative elements. So, from here now we can sum both sides for I is equal to 1 to d. So, here we get a I to the power p I is equal to 1 to d from by summing this side, and this side what we do, that this inside is sum over mod I is equal to 1 to d, okay, and then to the power p is there, and then whole thing, it does not depend on I. If I sum over I is equal to 1 to d, I just get n, correct, n number of these things are there. I should have actually I should have written typos. So, here it should be d, here it should be d. So, because there are only d number of components. So, here we would like to discuss everything in d dimensional space only, correct, because here d dimension, etc. So, here I should have written d here, d here. Okay. So, this is less than or equals to d times. Now, this whole to the power of p is there. So, what I do is that I change each and every mod ai by maximum of mod ai, okay, maximum of mod ai. So this term is independent of I now, okay. So of some maximum over all possible I, so that I replace here. So n is as it is and to the power p is there. So since that is the case, so I would get max of ai, and then this sum would give me another n, but p is outside to the power p, okay. So I would be able to write down then n into n to the p, that means n to the power p plus 1 times max of mod ai to the power of p. But that max of mod a to the power of p is less than or equals to mod a to the sum of all these, because this is after all for some I naught this is achieved, correct. So here I have written all possible these sums. So this is dominating this part. So in other words, what I have obtained is that I is equal to, so here I should write d here, d here, I is equal to 1 to d mod a to the power p is less than or equals to d to the power of p plus 1. So that is a constant, and then mod of n to the power p etc plus etc mod of a n to the power of p, okay. Okay, of course this is less than this is trivial, but what is important is that in between this part is lower bounded by this and upper bounded by this, okay. So because this part okay, so this would be used, okay. So from the functional stochastic differential equation, after taking the 2mth power of both sides of the functional stochastic differential equation, so then we get that there are how many terms, 1 2 3 terms, correct. So one term was a 0th term, and the integration b, and then another integration with sigma of sigma with respect to Brownian motion, and then we are taking norm etc. So we are using the triangular inequality. So after doing all these triangular inequalities and these things, what we are going to get left hand side is mod of norm of x t to the power 2m, and right hand side is less than or equals to c prime, this is just a constant, okay. So here norm of mod of x naught to the power of 2m plus norm of integration 0 to t b s x ds, here norm to the power 2m, here plus integration 0 to t sigma of s x dws norm to the power of 2m, okay. So we are going to get this inequality which we need to analyze next, okay. So why are we looking at this to the power 2m? Because we recall that the statement, here we are going to prove these things, right, to the power 2m, these things we are willing to prove. So we take this norm here for this reason. So now I need to upper bound these quantities, correct. So that we do now. First I consider this term. So we here use Helder's inequality as expected. So here 0 to t b s x ds, here norm to the power 2m, okay. This is equal to summation I is equal to 1 to d 0 to t. So here what we are doing is that writing the Euclidean norm here, okay. So Euclidean norm is, so here I can think m and 2 separately, this square and then m. So this square is the component square and then sum, and then so that is why we get this I is equal to 1 to d square of this integration, and then of course outside there is a power of m. Now here at this stage we use Helder's inequality. Here square of this integration is less than or equals to t times integration of the square, so that we use but then we take the summation inside to get square of the norm of b here inside. Okay. So, less than or equals to t to the m, this norm square ds, this to the power of m. Okay. So, this t comes out, so power m is there, so we get t to the power m here. Okay. So, now here we get this norm square integration 0 to t ds, and then we write down that thing, but here again we use here Hilbert's inequality. So, I would get here norm of bsx to the power 2m. So, I can either use Hilbert's inequality or I can use Jensen's inequality, because this power mth power is a convex function. So, only thing is that integration 0 to t is not an interval whose measure is 1. So, one has to reweight it. So, by 1 over t multiply and divide to, and then one applies that one can apply Jensen's inequality there to get that 2 to the t to the power of 2 m minus 1, that means to the m minus 1 additional term would come here. So, we would get this times integration b to the power 2 m ds. Okay. So, this thing is upper bounded by this quantity what we have obtained. Now, we go to the second term, the third term, but before that we take this sequence of stopping times. Okay. So, what is this? This is nothing but the exit time of the ball of radius k. So, whenever first time the process, the solution of the SD leaves the ball of radius k, that time is denoted by sk here. So, here we also know that since they need large time to exit, because if I write k is larger and larger, it takes larger amount of time to cross that with probability 1. So, therefore, limit k tends to infinity, sk goes to infinity almost surely. So, these stopping times are non decreasing and goes to infinity with probability 1. So, if I write on sk minimum t, small t, capital T, and then as k tends to infinity, that would converge to capital T with probability 1. Okay. Now, what we do is that we assimilate all these terms together as from the earlier slide here. So, this part I am going to use the new estimate. Here I would keep as it is for the time being. Okay. So, here I take S, and then I also vary S from 0 to t minimum sk. Okay. So, we will worry about it little later. So, let us see what is there on the right hand side. Here as before, x naught to the power 2 m and t to the power 2 m minus 1 integration 0 to t minimum sk norm b. So, here I am not writing it in full details, that it is also a function of u and x. Okay. So, the dependencies are omitted here just to put everything in the same line. Du, this integration where u is between 0 to t minimum sk. So, small t is fixed for us, k is also fixed for us. Okay. And then we are looking at the taking maximum over all possible s, okay, running from 0 to t minimum sk. So, what we are going to get is that that would be less than or equals to this t is fixed here. Okay. So, I mean earlier for s I should have got s here, but here I am taking in maximum between 0 to t minimum sk. And then, so here we get maximum 0 to t integration 0 to s minimum, because here this is a function of s. So, you remember that here for this we got this, but here we did not get any estimates for this. So, here if you have S, you would get S here, correct, exactly. So, that thing, but here for this case we can do that, because we know okay it is non-negative, is strictly increasing. So, we can actually for S also on the left hand side we can dominate it by T, okay, but there we do not know actually. So, here we have 0 to S minimum S k here to the 2 m and then max over 0 to T, clear. So, this is the inequality what we obtain using the earlier things.